I'm going to be explaining another approach for contrastive networks that we use unsupervised instance learning via nonparametric instance discrimination, and this is a positive sample. These neural net classifiers trained on data with annotated class labels can also capture apparent visual similarity. Can we learn a good feature representation that captures apparent similarity among instances instead of classes by merely asking the feature to be discriminative of individual instances? We formulate this iteration as a nonparametric classification problem at the instance level. So we have lots of instances. This is the problem that we face for word embedding, because in that case we had two different approaches like negative sampling, like hierarchical softmax, but we can also use noise contrastive learning like the approach of this paper. The goal is to learn an embedding without supervision. F theta is a deep neural network with parameter theta when mapping image X to feature. So this embedding would induces a metric over the image space. So this novel unsupervised feature learning is instance level discrimination, and we treat each image instance as a distinct class of its own. So you might expect that we have lots of classes, so we are in trouble. We are in the same trouble that we were, for example, in word-to-word embedding, that our denominator were too big. We couldn't do this, so we invented tools such as negative sampling, such as hierarchical softmax, or in this paper it uses contrastive noise, which is, it says, is it from model or from data? Is it noise or it is from data? So we create a memory bank because the number of instances is the same number of classes, so it's a huge number of classes. So we formulate the instance level classification objective using the softmax criterion. And under conventional parametric software formulation, for that image X with feature, the probability of it being recognized as ICE example is this probability given V. What is the probability of ICE example? But for non-parametric instance level classification, we can use the probability becomes like this, because what is the probability of given V? What is the probability of I sample? So we replace this with Vj transpose V and enforce it to be L2 normalization layer. And tau is just a temperature parameter. Then the learning objective is then to maximize the joint probability or to minimize negative likelihood. And then we have a memory bank. So what is the motivation for noise contrastive estimation? As I said, for word-to-vec embedding, we had problems because we had many classes, so invented things like hierarchical softmax, negative sampling. But here uses none of these approaches to deal with this problem, which is your denominator. That they created noise contrastive learning that says if something is based on the idea that good generative models should be able to distinguish data from noise. And a closely related idea is that a good generative model should be able to generate samples that no classifier can distinguish from data. This idea yields generative adversarial networks. This is the probability distribution estimated by the model is this one, and C here is explicitly introduced as an approximation of your partition function, this Z. So rather than estimating only the theta parameter, the noise contrastive estimation treats C as just another parameter and estimates theta and C simultaneously. And so the idea of noise contrastive estimation is that if we should discriminate between data and noise, and the motivation behind this is that we turn the problem into a supervision, into a supervised learning. So we adapt NC to our problem, and in order to tackle the difficulty of computing the similarity to all instances in the training set. We want to discriminate between data samples and noise samples. And Zi is your normalizing constant. We formalize this noise distribution as a uniform distribution. Following prior work, we assume that noise samples are m times more frequent than data samples. Our approximated training objective is to minimize the negative log posterior distribution of data and noise samples. PD here is the actual data distribution, and Pn is for the noise. And computing normalizing constant Z sub I, like this, is expensive, so we follow and treat it as a constant and estimate it via a Monte Carlo approximation. But we also use the proximal regularization because unlike typical classification setting where each class has many instances, we only have one instance per class. And during each training epoch, each class is only visited once. Therefore, the learning process oscillates a lot from random sampling fluctuation. We employ the proximal optimization method and introduce additional terms to encourage the smoothness of training dynamics. As learning converges, the difference between iterations gradually vanishes and the augmented loss is reduced to the original one. So as you see, this is the effect of proximal regularizer. Then as training iterations increases, the training loss for different hyperparameters, you could see the effect of proximal regularizer. But to classify test image, we first compute its feature and then compare it against the embedding of all images, which is quite hard in the memory bank, using that cosine similarity. But we don't do for all of that, we just do for top k nearest neighbors, denoted by n. It would then be used to make the prediction via weighted voting.